Hi, everyone. My name is Akila Balasubramanian, and I am a principal engineer working on applying large language models on real production systems. As I was applying more and more LLMs to my day-to-day job, there is one thing that I realized pretty quickly. Sending more data into the LLM does not necessarily mean that you will get the best outcomes. And in fact, it does the opposite. If you feed the LLM with more and more data, as you approach your context limits, or as you end up diluting your signals, you might get unhelpful responses. So that led me to take a step back and ask a different question. The question is not how to get a good response from the LLM, but how to improve the data that I'm feeding into the LLM, which will in turn improve the outcomes. So that's what this talk is going to be about. And if you think about it, we have a lot of noisy and high volume data that we operate on a day-to-day basis. And just directly sending this raw telemetry into the LLM is not going to be helpful. So with that context, let's dive right in. So I'm going to be using observability for my case study, but I want to make one thing very clear. This problem that I'm about to talk about is not specific to the observability domain. It is every system that basically deals with large noise and highly unstructured, high cardinality type data is going to be running into this problem. That could include large documents, your RAG pipelines, or your analytics pipelines, or like any logs that you're dealing with on a day-to-day basis. If you think about observability specifically, in modern distributed systems, there are thousands of entities that are emitting metrics, logs, and traces on a continuous basis. And these entities range anywhere from your services to your containers to endpoints and so on. Now, if this raw telemetry, high cardinality signal or time series data is directly fed into your LLM, it's definitely going to be a very challenging problem, and you might run into three potential issues. The first one is token overload. All of us know that LLMs have a fixed token budget, and all of this real data, you're going to using up your resource. And one thing you'll end up doing is truncating your data, which results in signal loss, because you might end up truncating stuff and like anomalies and change points that are key to identifying the root cause of your problem. And that eventually results in inconsistent outputs. So it is largely dependent on whether a data point made it into the LLM or not. If it does, your outputs are great. If it does not, your outputs are meaningless. So let's look at how this actually works in a production environment. Here, I have an example of a bunch of time series data that were emitted from real systems. On the left-hand side, you can see that we have some latency numbers from multiple services. We have restart signals from pods and also error rates from services. And this is like a truncated version from about 2,000 plus time series data emitted by a real production environment. And this is, in fact, a small slice of data that only represents the last 10 minutes. As a human, when you take a look at this data set, it's pretty obvious that the latency for service B has jumped from 100 milliseconds to well over a second. And during this time window, there has also been an increase in the error rate. And you also see associated pod restarts going on. So it's very obvious that something is not right. But when this information is given to the LLM, says that there was no dominant anomaly detected. This is because the attention is distributed across all the signals. It's not because the LLM is not able to reason, but it's not able to identify the right signals to reason on. So now the question becomes not if the LLM is giving you the right answer, but if the LLM was provided the right signals to do reasoning on. So going back in this example, we see that it actually missed. If you look at the right-hand side, it actually says the root cause is unclear with very low confidence, and it completely missed the actual spike with service B. It missed the restart signals with pod D. It completely downplayed the anomalies, and it spread the attention across signals. So this is a very small example, but if you were to take a step back and look at the whole production system, the scale is going to be massive. You will ideally have thousands of entities, which include services, pods, containers and endpoints emitting all of your metrics and logs. And on a continuous, the state of these systems are changing with time. So if you take all of this raw telemetry information and feed it into the LLM, you're going to run out of context pretty quickly. And the cardinality is super high. You not only have a lot of entities, but you have a lot of dimensions that the LLM has to sift through and figure out what the anomalies and change points are. And if you think about it, in a real production system, things are changing by the minute. So what a snapshot of a system a few minutes ago is very different from the snapshot that you're observing right now. So you have a lot of data, you have a lot of signals, which are continuously changing, and you're required to press it in a way that the LLM is trying to understand. This can be a very hard problem. And then, like I said before, it's not about the LLM's ability to reason, but it's about the it's about our ability to pass the right signals to the LLM to allow it to reason in an effective manner. So the key takeaway here is raw data. It's not just observability data, but any noisy, high cardinality data is inherently not LLM ready. And we should stop fitting data into the LLMs and instead take a step back and think about reshaping this data to allow the LLM to reason better. That brings me to semantic condensation. What is semantic condensation? Semantic condensation is a token-aware transformation layer that basically accepts high cardinality time series data and converts it into truth summaries that can fit into the LLM's context. It serves as a bridge between raw numerical data that LLMs could inherently find difficult to process and converts it into a format that is digestible and more easy to reason on. So what this gives you is a bunch of things. One is token awareness. The actual important data set is being optimized in a way that interesting signals are surface easily, and they are limited to the context window of the LLM. Second, semantic coherence. This condensation is done in a way where we are able to preserve the signals and also the relationship between the signals. So all of this is not done in isolation, but in correlation with other signals in place which are available in the data set. And finally, operational fidelity. It retains just enough detail to pinpoint the root cause of the issue. So how does this work in practice? Semantic condensation is a multi-stage pipeline. And all we're doing at every step is to make sure that the noise is removed, but the meaning is also preserved. So a raw time series in this example that we saw before is fed into this pipeline, and it operates in 4 stages. In the first step, a pre-analysis is done. And the goal here is to do basic statistical analysis. This could include finding interesting anomalies, change points, what your mean is, what your variance is, identifying patterns and sequences and correlation. And once this pre-analysis is done, it gets passed on to the next step, which is importance scoring. In this case, in the first step, we have condensed the data into interesting signals. But now we need to tell the LLM what is important and what actually matters. And this is done by scoring all of these individual time series. And there are several parameters that get taken into account. Once the scoring is done, the next step is an adaptive token budget tiering. If you think about it, LLMs have a limited context. So what we do differently here is we treat tokens as a budget that gets allocated deliberately. And the goal here is high information signals get more space in the context, and low information signals are not completely truncated, but they have just enough context to present the full picture to the LLM. And finally, the last step is trend classification. Once all of these numerical patterns are identified, we translate them into a language that LLMs can understand better. LLMs can reason over semantic descriptions better than non-numerical data. So what we do is convert this into semantic labels, and there you go. This raw time series gets processed and converted to a semantic digest, and this is what gets fed into the LLM for summarization. So the goal here is to strip out the noise at each stage and preserve operational semantics in a manner that makes reasoning more effective and reliable. So let's look at each key idea that has been talked about here. The first takeaway here is if you know that a specific computation can be done deterministically, then do not use the LLM for it, was the first key takeaway. So if you think about it, LLMs can operate with numbers, but when you feed like raw telemetry data, we are inherently telling the LLM to do all of this processing, which includes anomaly detection, change point detection, and pattern matching, trend analysis, and then summarize it all in a single step. That is a lot of work. And the problem only becomes worse if your size of the data increases. And for a domain like observability, where things are continuously changing and data gets emitted by systems every minute, this is a very hard problem to solve. So in this step, the key takeaway is we do all of the computation outside of the LLM. And by the time the LLM gets to see the data, everything has been processed, all the anomaly has been pre-flagged, and that also helps to improve the latency and the determinism of this approach. The next key idea is to guide the attention of the LLM. LLMs inherently do not know what to focus on. If you provide a lot of data, it's going to spread its attention across everything, but that's not what we want here. We want the LLMs to know what to focus on, and we want the LLM to be able to use this information to make that decision. So here, when we score these signals, we score them based on anomaly severity, based on rate of change, cross-signal correlation. The key thing here is each of these signals are not scored in isolation, but they are scored in relation with other signals and other anomalies that were discovered during the live incident. And finally, we also take entity criticality into account, like how important is a specific entity which will cause the signal to be scored higher. And once the scoring is computed jointly for all signals, this becomes a great space to process that raw data and only elevate things that really matter. The next key idea is adaptive token budget tiering. So once we have figured out what the scores are, we need to be able to fit that information in a limited context window that the LLM has. And all of us know that LLMs are constrained by windows, context windows. So we have to do the best that we can to surface as much information as possible and operate under this constraint. So this is done by taking a tiered approach. Let's say I have about 100,000 signals coming out of the previous step, and each of this has been scored based on importance. In this section, what we do is we take a tiered approach. There are 3 tiers in the mix. The first tier is the detail tier. So high importance signals land in this tier. And the goal is to make these signals as descriptive as possible, because clearly there are interesting things going on here, and we want the LLM to be aware of this information. The second tier is the compressed tier. It is not as detailed as the first tier, and it provides a more compact representation, but it still preserves key inflection points. The third tier is the minimal tier. So instead of blindly truncating things that don't matter, we move them to the third tier, which is the minimal tier. And the goal here is to keep very minimal summaries that do not consume the budget. So this allows us to capture the full state of the system and represent it in a format that does not reduce the meaning, but at the same time eliminates the noise. The last key idea is to translate this into a format that allows the LLM to reason better. LLMs are better at reasoning with semantic descriptions rather than numerical patterns. If I give a numerical pattern to the LLM, I'm inherently asking the LLM to figure out all of the correlation and then tell me the final outcome. But instead, if I'm able to translate this numerical patterns coming out of the previous steps into a semantic label, that allows the LLM to understand this because that's what it's trained to do. So these examples of these semantic labels could be stable behavior or anomalous spikes, or even a recovery pattern. Like you could have a time series where things were going wrong, but suddenly you see an improvement. Like you could have a high CPU utilization and suddenly you could see a drop, and that signal indicates a recovery pattern. Or it could be like a degraded performance where things were performing very well, but now you see an increase in memory usage or CPU utilization, for example. So this way, you're not just sending the numerical data, but you're able to map them into semantic labels that the LLMs are trained to reason out better on. So at this point, the natural question to ask is what gets preserved and what gets compressed? Because we could have these important signals, but how do we decide what is important? So the key thing here is to keep spikes, dips, and distributional shifts, because these are interesting points that I'm going to tell you what is wrong with your observability system. The second thing to preserve is change points. These change points tell you when something started to go wrong, and they are very key to determine the root cause of a problem. And the third thing to preserve are operational patterns. These operational patterns tell you the full picture. And at this point, you're just looking at the full story of when something happened, why it happened, and you're not just focused on point in time isolated events. So this allows you to get a full picture while also making sure that all of the noise is eliminated. So let's look at the previous example that we referred to. On the left side, we have the same familiar time series that we looked at, and we could see the LLM output. On the right, at the top, we see the same information that was sent earlier, but this time it is looking better because it has been condensed using semantic condensation. This is the semantic digest, which approximately takes about 4,500 tokens, which is so much better than sending hundreds of thousands of tokens generated from raw telemetry. In this particular digest, it's very easy to see the signals very clearly. The latency spike in service B is obvious. The error rate increase is also obvious, and it's able to correlate this increase in latency and error rates with pod restarts. So the global observations indicate that there is a primary anomaly in service B, and when this information is passed to the LLM, the output clearly states that the root cause is service B degradation, and the confidence is really high. Now, when you compare this with the previous output that we received, because the LLM had to do this processing on its own, the attention was distributed across all the signals, and the LLM could not clearly identify the root cause. So at this point, a natural question to ask is, why not use the existing traditional approaches? Why use semantic condensation? Traditional approaches like downsampling, aggregation, raw truncation exist, but they don't necessarily exist for the purposes of removing noise while preserving meaning in a way that allows the LLM to reason. And that's the key difference here. Now, if you look at downsampling, for example, it definitely reduces the volume, but it discards all of the short-lived spikes. And for a domain like observability, these short-lived spikes are going to be critical to determine the root cause of an incident. And moving on to aggregation, aggregation generally smooths your data, but the bad thing is it obscures or flattens your variance. And at the end of the day, you lose the temporal structure of the data. Raw truncation is great for reducing the context window, but you could end up pushing critical events out of the LLM's view. So the LLM can only act on what it can see. And if it's not able to see important data points, it's not able to give you that output. Semantic condensation takes a different approach. It is designed for LLM reasoning and not for dashboards. It is able to preserve anomalies, change points, patterns, and transitions. And it maintains a coherent operational narrative. We are not looking at signals in isolation, but we are looking at signals, correlating them with each other. So the goal here is not just to mindlessly compress, but it is to compress in a manner that makes reasoning more easy and reliable. In terms of testing this out, I tried this approach with about thousands of time series data in a real production environment. And one thing I could clearly see, and I was also trying to test it based on 3 factors. First is scale, efficiency, and accuracy. In terms of scale, this approach was able to handle thousands of concurrent time series in a real production environment, which is very promising. In terms of efficiency, there was an order of magnitude reduction in the tokens, as opposed to sending raw telemetry directly to the LLM. So this also helps to reduce the cost saving. And the third is accuracy gain. I saw at least 25 percentage points increase in the troubleshooting accuracy. In the old approach, the LLM was struggling to pinpoint the root cause, but with this semantic digest in the mix, the accuracy of the root cause greatly improved. Now, when we take a step back and we look at the problem, we can actually design an LLM-ready telemetry pipeline. And there are 4 key things to take into consideration here. First, pre-compute at digest. Semantic condensation does not necessarily have to happen at query time because that could increase your performance latency. And this could happen at ingest, which helps to keep your latency budgets in control. Second, score contextually. Important score, like I mentioned before, is not generated in isolation. It is done in the context of the current incident. Third, tier dynamically. This token budget need not be fixed. It definitely depends on the context window available to you and the nature of the model that you're using. And fourth, validate coherence. Before passing this digest to the LLM, I was able to ensure that this input is inherently coherent because only when the input is coherent, the output from the LLM is going to be reliable. So taking a step back, this helps us build a new abstraction layer for observability. Semantic condensation is not just a compression step, but it is a purpose-built semantic interface between your data systems and your reasoning systems. They provide semantic consistency, which means like all of the digest itself is inherently coherent. It is able to preserve the key signals in a way where the noise is cut down, but it also helps to keep the LLM's reasoning ability intact by surfacing important signals in the output. The second thing is token efficiency. We get an order of magnitude reduction in the token, and we don't lose out on important information. And this is designed for real production systems and not just research benchmarks. So if I had to give you some takeaways to take back to your team, first is raw telemetry. In fact, not just raw telemetry, but any noisy, unstructured, high volume data is not inherently LLM ready. You need to apply some sort of transformation before you send it to the LLM. And semantic coherence beats any normal compression strategy out there because you're not just focused on cutting down the noise or the tokens, but you're doing it in a way that helps to allow the LLM to reason better. And importance scoring is the key factor over here because that gets to decide what the LLM sees and what it gets a minor context about. This goes back to the 3 tiers that we saw. In the detailed tier, the signals had a lot of structure in them and a lot of details for the LLM to take a look at. The compressed tier had a more compact representation, and the minimal tier had minimal summaries, but just enough context to allow the LLM to reason better. And this helps to build a new interface layer between your data systems and your reasoning systems. So if there's one thing that I would like to leave you with in this talk, LLMs don't always fail because they can't reason better. They fail because we don't pass the right signals to them to reason on. So when you take a step back and you fix your input, you also fix your outcome. Thank you.